Hi Frank, nice to see you again. We are talking about Kiutra this time. Could you tell me what are your biggest takeaways from the Kiutra interview?
Yes, I had 4 lessons. I really liked the interview. It's a really special company, and what I liked also. Oh yeah, so what did I learn? The first thing what I learned was the importance of cryogenic cooling. So without cryogenic cooling, it's not possible to do spin qubits and superconducting qubits. So that was lesson number 1. Lesson number 2 was that okay, you cannot do without, but with cryogenic cooling, you also create 2 important bottlenecks. And the first bottleneck is if you produce a chip, you also need to test it. But in order to test if it's with just a fabrication, you don't know if the chip is working. And superconducting are really fragile physical systems. So if you want to test them, you also need to cool it. And current cryogenic cooling systems are very slow. Sometimes it takes more than 6 hours to a day to test it. And that is a massive bottleneck. Kiutra has a solution for that. They claim that they can do the testing 6 to 10 times faster than the current cryogenic cooling systems. So it's the testing is a problem, and also the heat is a problem. So as you scale the amount of qubits, each qubit has roughly 3 control lines. But the problem is you have a very limited energy budget, and it's about millikelvin temperature. It's about microwatts, and it's really small energy budgets. But you can. One analog is, for example, that you sit in a room that you try to cool, but you have pipes with hot water coming in. and that those hot pipes, though, they prevent the room from getting cooled. And the problem is as you scale the amount of qubits, then more of those hot pipes are coming into the room, and that's a problem, because if you have too much heating, then the state collapses. So then you need really cold temperatures for the superconducting and spin qubit for the quantum effects to happen. Now that are 3 lessons. So that were the first 2 lessons. The third lesson is that I thought that cryogenic cooling was only for spin qubits and for superconducting qubits. What I learned in the interview is that it's also helpful for ion trapped and for neutral atoms. And why is that? For example, ion trapped, if you trap the ions, if you cool everything down, the environment is cleaner and you have less errors. And the same is for neutral atoms. Neutral atoms, you cool down the atoms with lasers and vacuum chambers. But those vacuum chambers, if you cool them down, then you have less errors. So, and this was really nice learning. I wasn't aware of that. And the fourth lesson that I had is the importance of helium-3. And helium-3 is a byproduct for nuclear bombs, and therefore it's quite scarce. So the CEO of Kiutra, what he explained is he said, if you really want to, if quantum computing really scales, and if it really uses a lot of cryogenic cooling, there's not enough helium-3 on Earth. So quite soon we run out. But that's one problem. But the other problem is who has the inventory of helium-3? That is the US and Russia. And you could ask yourself, from a geopolitical sovereignty, do we really want to be dependent on those 2 countries for our compute? And probably the answer is no. So that were my 4 lessons from the interview.
And what does Kiutra actually do to solve this problem?
Now, what Kiutra does is what they have is they make cryogenic cooling. And within cryogenic cooling, they use magnets to cool down with the cryostat. And so they have 2 stages. In the first stage, that's similar to normal cryostats. Then they bring it down below 4 millikelvin temperature. And the lower you cool it down, the harder you need to work. The harder it is to cool it down. I didn't know that. So it becomes significantly harder the cooler you want to make it. But they have a they use magnetics, and with that they create magnetic fields, and they use that to cool it down. And because of that, they're helium-free. But normally with magnets, then it's a single use. And what they do, they make it continuous. And how do they do that? They use multiple stages, and then they rotate. And with that, they make it continuous. So that's the first thing, no helium. And the second thing is, so on the bottleneck, is the testing, they said, okay, they have a sample tester. So what they do is they create a modular approach, and they don't have to cool down the total machine. So they cool certain parts of the machines, and certain parts can be cooled less, and certain parts have to be cooled more. So yeah, what is the right word for that? It's not complementary. It is if you have different buckets. Now, that is what they do.
I understand what you mean.
And the second thing is they automated the testing. And because of that, they can do it much faster, 6 to 10 times faster than a normal cryogenic cooling approach. So with that, they solve important bottlenecks.
Okay. Can you explain a bit the heat budget, what that is in simple terms? You were talking about it.
The heat budget is how much heat can you tolerate in the system. So you have the cryostat, and inside the cryostat is the chip, but the chip, there you have the Josephson functions, and those create the superconducting for superconducting qubits effect, or for spin qubits. There the effect is trapped. But if you really want to exploit that, you need to have a connection outside the cryostat. And that is done with normal measurement equipment. But to connect that, you need a cable, a control line. And you need amplifiers, you need control lines, you need control measurement. And all those elements, they have heat. And heat could create disturbances and could disturb the coherence of the qubit. And if that happens, then the state collapses, and you no longer have the effects that you want. So it's very important to cool everything down. But the heat budget is, how much can you cool? And maybe to give an example, I think it's in AI, you're at room temperature, and there you cool. They also need to cool down the GPUs. But the energy budget is like 10 billion times difference between AI and quantum technology.
Okay.
And so that's really the heat budget. So how much? So the control lines that go into him, they can also not consume a lot of energy. Because if they consume too much energy, it produces heat that destroys the state.
And if I understood you well, usually they use helium-free to cool down, but helium-free is an issue, and you said Kiutra does not use it. They don't use it at all?
They do use it for the I think they use gases. I don't know. I'm not 100% sure if it's helium-3, but they have a pre-cooling, and that's a stage where but that has every cryogenic computing company. They use that to cool it down below 4 millikelvin, and from 4 millikelvin to cooler, so to 20 millikelvin, that's where they use the magnetic approach. And there, in the magnetic approach, that stage, no helium-3 is being used.
Okay. Could you explain a bit more what magnetic cooling is?
Yes,
I think you mentioned a bit about it, but
I think what is really cool is they make a magnetic field, and with that magnetic field, when they put it on, then the atoms in that magnetic field are being ordered, and then it releases heat, and then you turn off the magnetic field, and then the heat is being absorbed, and in that way they cool it down.
no, difficult to imagine how that works, but
yes. But I think those things are quite cool, and I'm also proud that there's a small European company working on those problems. And one reason I think it's also cool is when I interviewed Emergence Quantum, Thomas Oakley, it's the CTO, and it's an Australian company. And one of the things that he said is that before we go to quantum computing, between AI and quantum computing, he thinks there's a stage in between, a tectonic shifting compute, cryogenic compute. And he said if you cool down the chips, then you can overclock the chips. And that also brings important benefits. So he was talking not like a clean room, but a cooling room. So I found that funny.
Okay. What is Kiutra's first commercial wedge?
Now the competitive advantage that Kiutra has is, first of all, lower geopolitical risk. So if you're a government and you have a program for the army, and you want to have quantum computing, then I think it's helpful that the geopolitical risk are lower. That's the first one. The second thing is the testing time is significantly faster. And because they have a modular approach, they can choose between the size and they can separate different parts of the quantum computing. For example, maybe control electronics you don't have to cool so much. The chip you need to cool a lot, and maybe the cabling you can cool down less. So they can split that. Whereas at the moment everything is one size fits all. That's the first one. The second thing is they automated the testing, and third they created stages to make the magnetic continuous.
What is the importance of testing being automated? Is it such a big bottleneck, and why?
Yes, it's a significant bottleneck. If you produce a chip, you can produce maybe multiple chips, maybe 1,000 chips a day, depending on how you scale it. If you go to a foundry, and typically quantum technology is not in the stage where there's mass market production, it's more R&D phase. But in the future, for mass market, imagine you produce 1,000 chips a day, or 100 chips a day, and that if you want to test one chip, that it takes 2 days. That is then a significant bottleneck. Also on testing, you can maybe test one chip at a time. If you needed to use the total cryostat to test it and to cool it down, and that's really a problem. So if you can reduce the test time from, let's say, 1 day or 2 days to a few hours or maybe 10 minutes, that's a massive time gain. And when after you tested it, you get learnings. and those learnings that is maybe also determines your speed of innovation.
How does this compare to companies like Orange Quantum Systems or Quantum? Are they competitors, or are they
I feel they're
doing a
complementary.
different kind of way of cooling?
Yes. Now, Kiutra really does the cryogenic cooling. What Orange Quantum System does is really the testing. They automate the testing. They build software programs where they tune and they test everything. And Quantum Map, what they do is they have a squid, and with the squid, a ring, a quantum sensor, they create certain maps, and with that maps they can identify errors while the chip is still running. And that does not impact. So with Orange Quantum System, when you make a measurement, then the state collapses from probabilistic to either 0 or 1. But with Quantum Map, you can see certain patterns, the magnetic flows, and with that you can identify errors which you normally cannot see. But without taking the measurements, so without the chip collapsing to 0 or 1. Is that a clear explanation, Henny?
They all three address testing from a different angle, if I understand it well.
Yes, that's correct.
Okay. And what is the long-term opportunity beyond testing for Kiutra?
Now, if we talked a little bit about it, if there would be between quantum computing and AI, if you get cryogenic computing, that would be helpful, but not required. And given the complementary, that they make different sizes, therefore they can also expand the market, and that it might enable them also to make the infrastructure ready, cooling ready, if it would fit into a data center.
Okay, so this could become like data center cooling for quantum.
Yes.
Which would be probably a huge mass market.
Yes.
For which quantum technology is Kiutra most relevant? Is for all?
It's most relevant for superconducting qubits and spin qubits. But I was also surprised that it was also useful for ion trapped. And why is that? For ion trapped, you have less motional heating because the ions are trapped in magnetic fields, and tiny electric field noise from the metal trap electrodes can shake the iron, motion heating, and that now is prevented. You have better vacuum, you have less black body radiation, and what that basically means is warm objects emit terminal radiation at room temperature. The trap emits infrared black body radiation, and if you cool it down, then that is not the case.
Okay, so Kiutra does not depend on superconducting and spin qubit training. They have much more, what do you call it, irons in the fire, we would say in Dutch.
This is what I learned. However, the truth is that the cooling is much more significant with superconducting and ion trapped. But if those will not materialize, if let's say neutral atom would be a winner or ion trap would be a winner, I think it can still be helpful, but you might require less cooling.
Okay. You talked about cryogenic compute. Is that a bit more like an intermediate market for them before quantum really takes off?
I don't know. I'm a bit surprised by the speed of adoption of quantum computing. I now roughly look at it for 2 years, and there are significant improvements. But also, the more I look at it, the more I realize how many bottlenecks there are. So it's a bit, I find it very fascinating. But when I started looking at it, I was thinking what you need for useful quantum computing is 2000 logical qubits. But the first applications are at 100 logical qubits. And my estimate was 100 logical qubits. We reached that around 2030. And then I thought a wall of money and talent is coming in. However, if you look at the roadmaps I interviewed a few weeks ago, I interviewed Inflection. They target 100 logical qubits in 2028. This week we had Quantinuum going to the stock market. They had their first listing, an IPO, and they also target 100 logical qubits by 2028. So that's 2 years faster than I expected it to be. And yeah, we will see what will happen. Maybe those roadmaps are too aggressive and they could set themselves up for disappointment. But if they deliver and execute on it, then it will be, quantum will be faster. And also I think much more money is at the moment much more money and talent is moving into quantum technology. I don't think there's a lot of money going into cryogenic compute. So from that point of view, if you judge based on money and talent, I would bet on quantum being faster. But yeah, we see.
Okay, that sounds logical. What sectors and companies should investors watch after this interview?
I think what is interesting is that if Kiutra, if they deliver and execute, it's quite positive for superconducting and spin qubits. But it can also be an important enabler for ion trapped and neutral atom. So that's it. The other thing is, if one important bottleneck is being solved, it increases the probability of superconducting and spin qubits winning. So that is important for Orange Quantum System, Delft Circuit, Quantware, Quantamap, all the companies in these value chains, in those supply chains.
Okay. What investment implications have the learnings you made from this, or you took from this interview?
The most significant implication is that I is the importance of cryogenic cooling. So the investment implication is, I think that it is cryogenic cooling is an interesting investment opportunity. And I did not fully appreciate that. And now I'm more positive about cryogenic cooling and the role that it plays and the bottlenecks that it is solving. And I think it's an important bottleneck that needs to be resolved. And Kiutra has an interesting roadmap to solve those problems.
What are the main risks for Kiutra?
The risks are that they don't execute on the roadmap. Maybe that helium-3 gets more available. Blue Force, for example, on social media they say, okay, we go to outer space to harvest helium-3. So maybe there are alternatives to get supply for helium-3. But also it could be that superconducting or neutral superconducting spin qubit will not be the winners. So is photonic or ion trapped or neutral atom, if those win, or if a competitor of Kiutra wins, let's say Blue Force or Leiden Cryogenics, if one of those win, then that would be not good for Kiutra.
What would help to increase your conviction in the success of Kiutra?
Now, Kiutra has two important prototypes. One prototype is about getting really fast sample testing. And the other one is about very large, basically the infrastructure for the data center cryogenic cooling. If they execute on those two products, and I think the type names were L and X, if they execute on that on the roadmap, and if then my conviction on Kiutra would go up.
Okay.
And the other thing, of course, is if the probability of superconducting and spin qubit winning, that also is very helpful.
What should investors remember from this Kiutra interview?
I think for all investors looking at superconducting and spin qubit, I think the heat budget is very important. So that is a bit a trade-off. So if you scale the amount of qubits, then you get more heat into the system. And that is so. On the one hand, you need cryogenic cooling, but on the other hand, it also creates bottlenecks. And that is important that gets solved, and therefore cryogenic infrastructure is important. So have a look at that. That's an important bottleneck. But the other hand, it's also it enables. It's a big enabler. It's lowering. It creates the superconducting effect, and also for ion trapped and neutral atoms, it's an enabler of lower errors. So that is interesting.
Okay. Well, I think we have come to the end of our exchange. Thank you for this interview and for the learnings you shared with us.